Hi everyone, bonjour. Welcome to the IB Crocodile. Today I'm going to continue a series of videos on differential equations according to the IB math analysis and approaches, the higher level content. In a previous video, I started to talk about differential equations and I talked about the first type of differential equations, which is the separable ones. Today I'm going to continue. I'm going to present the second type of differential equation. As you know, according to the IB math analysis and approaches, on the higher level, of course, you need to be familiar with four types of DE. Separable differential equation, homogeneous differential equation, first order linear differential equation, and the numerical approach or Euler's method. For more information, I will leave a link for the previous video, and you can watch it and to get the full picture of this series. Okay, so bring your pencils and let's get ready. Here is the general form of homogeneous differential equations. dy by dx is equal to a certain function in x and y, where that f is a homogeneous function or homogeneous function. So let us remember what is a differential equation. Differential equation is an equation where you can find any sort of derivative, you know, like dy by dx, d2y by dx squared, the third derivative, right? So any equation, you know, with some sort of differential or derivative form is just simply called a differential equation. And the solution of the differential equation is to find the function y as a function of x that satisfies the differential equation to start with. So one of the types, so the first actually, like the main technique or the main art to solve any differential equation is to know first what type of differential equation we are looking at. So as I mentioned in previous videos, you can check the separable differential equation. Now today I'm going to discuss with you, okay, the homogeneous differential equations, and this is the general form. So every time you see this form here, you may think, okay, it might be homogeneous differential equation if this function here is homogeneous. So now the next question here, what is a homogeneous function? So homogeneous function by definition is homogeneous of certain degree n if f of tx ty is equal to t to the power of n, you know, times f of x and y, where n is an integer. Now let's have an example just to, you know, to see what I am talking about. So let's say, for example, we have a certain function here, f, x, and y equals to 2x squared y minus 5x cubed plus 7xy squared, right? So what I'm going to do here, first I would actually try to find what is f of tx and ty, right? So let's find that. So f of tx, comma, ty, it means I'm going to replace each x by tx, I'm going to replace each y by ty, right? So it's going to be 2 multiplied by tx all to the power of 2 multiplied by ty, right? Because we have y there. And then minus 5, and instead of x, I'm going to say tx all to the power of 3. And then plus 7 times tx, and then times ty all to the power of 2. Okay, and now let's do just some simple manipulation here. So we can say, okay, so this is 2, and then we have t squared. Okay, I can do it even step by step. Okay, 2t squared x squared, and then times ty minus 5 t cube x cube plus 7 tx times t squared y squared. Okay, so we can even simplify more. So we can say, or I can just take t cube common factor if you like. So if I take t cube common factor, you know, see here t squared times t is t cube So what is left is 2x squared y. And then if you take t cube from the second term or divide basically by t cube, so you end up with 5x cubed. And then plus the third term, if you take t cube or t to the power of 3 common factor, you end up 7xy squared. Okay. Now, if you compare now this with the original function, we came back to the original function. So you can say, okay, this function is homogeneous. Okay. And the degree here is third degree. The third degree homogeneous function, because we could apply this definition here on this function here. So this is the first step. Yes, dy by dx, if the function on the right hand side is homogeneous, so this is basically will be a homogeneous differential equation. Okay. Now there is a simplified form. Okay, so the previous form was the general form. This is the definition according to the textbooks, right? Homogeneous function. But then there is a simplified form that helps you like get or identify the homogeneous differential equation probably much easier or much faster. So the simplified form says a differential equation is called homogeneous if it can take the form dy by dx is equal to f of y on x, okay, or y over x. Okay, so if you could rewrite differential equation in this form where you have dy by dx by itself on the left hand side, and you could see a certain function in y over x on the right hand side, so you can also say, yes, this is a homogeneous differential equation. I have a couple of examples here. Let's go through them just to get a clearer idea. So we have here, okay, we have dy by dx on the left hand side is already there, but on the right hand side, so I can rewrite this as, okay, dy by dx is equal to, actually I can split if you have from the numerator, if you have negative and positive the numerator, so you can split, right? So you can say, okay, so this is x squared over x squared minus xy over x squared plus y squared over x squared, right? So this will cancel out, so you end up with 1, and then minus, okay, I can cancel x with the square down here, so you have y over on x, okay, and then here I can rewrite this as y on x all to the power of 2. So once I could rewrite the dy by dx as a function of y on x, so this is the green light to me for a homogeneous differential equation, and then I will explain, okay, how to solve this type of differential equation. Now, the second example here, okay, we have dy by dx is equal to x squared plus y squared over xy. Allow me to do to divide both numerator and denominator by x squared, just to as an algebraic manipulation here. So I will divide x squared plus y squared over x squared, and then divide here xy over x squared. So you can divide, both numerator and denominator by the same term. That's fine. So then you will end up with on the numerator we have 1 plus y on x all to the power of 2. Okay, I just split here. Okay, positive, so we have x squared over x squared is 1, and then y over x all to the power of 2, right? And then at the denominator here I can cancel the square with the x up here, so we end up over y on x. Again, I could rewrite it as a function in y on x, so this is a homogeneous differential equation. Okay, so let's now have an example here. This problem actually is an IB past paper, and let's have a look at this question here, so I can show you the approach while solving this question. Okay, so solve the differential equation. X squared dy by dx equal y squared plus xy plus 4x squared, given that y equal 2, when x equal 1, give your answer in the form y equal f of x. Now, sometimes, the question may mention to you, this is homogeneous equation, but sometimes, you don't see the keyword. So you need to build the skills to be able to know or to recognize that, yes, could be a homogeneous differential equation. I mean, first of all, if I think about this equation here and I think about the separable, now we have two forms of separable differential equations. If I have two functions multiplied by each other, like f of x times g of y, or divided by each other, this is the two forms, but I don't see them here, right? And so let's try and see if we could rewrite this as a function of y on x. If so it will be homogeneous equation. Okay. So what I'm going to do, I'm going to divide both sides by x squared. So I end up with dy. Why? Because I want actually to have dy by dx by itself, because this is the form, right? So here we need to respect the form. We need to follow the form. Dy by dx, so nothing is attached, nothing is multiplied by dy by dx, and then we have f of y on x on the right hand side. Okay, so let's do that. So I divide by x squared, so I end up with, okay, y on x all to the power of 2, if you like, and then plus xy over x squared, and then plus 4x squared over x squared. Okay, so I can cancel here, right? And then I can say, okay, dy by dx is y on x all to the power of 2. I can cancel x with the squared, so we have plus y on x, right? And then plus 4, which is great. Now I could prove that this differential equation is homogeneous differential equation. Now, what is the approach? Now, the approach here, I'm going to replace y on x and give it a certain variable, right? Let's say v. I mean, v is like the most common variable in textbooks. So I'm going just to follow the textbook, not to confuse you, right? So I'm going to say, okay, let y on x equal to v. So this is your first step. And okay, so what we can do here, we can say, okay, if y on x equal v, that implies y is equal to x times v, cross multiplication. And then I need to find dy by dx in order to replace, okay, dy by dx on the left hand side. Okay, what to replace with. So here we have x times v, but actually we are differentiating with respect to x. So I'm going to use implicit differentiation with actually product rule, because I have x times v, so I have two functions, right? So we're gonna use the product rule. So what I say, the first, which is x, multiplied by the derivative of the second. Now the second is v, so basically is 1, but because v is not x, basically is not function of x, so I have to multiply by dv by dx. Okay, application of the chain rule and implicit differentiation, and then plus v multiplied by the derivative of the first, which is 1, because here x is just derivative is 1. Okay, so this is basically every time you see homogeneous differential equation, you're gonna actually follow exactly the same 3 steps there. Put your substitution and then find dy by dx. Okay, so let's do that. So I'm going to substitute now in the main differential equation. So I can say, okay, so this is x dv by dx plus v. I mean, v times 1 is v, right? And then on the right hand side, I can actually replace each y on x by v, right? So we have here v squared plus v plus 4. Now this approach here allows me to transform this equation somehow into a separable differential equation. Okay, so I can deal easily with. Okay, so this is really the main target of this approach, to convert or to make it a separable differential equation again, so I can easily deal with it. Okay, So here we have plus v and plus v on both sides, so I can cancel them if you allow me, right? And then I can say, okay, so I have x dv is equal to v squared plus 4, all times dx. Okay, so this is a separable equation because we have function of v, a function of x, but all I need to do is just to bring the v with the dv and x with the dx. I just put dx here on the right hand side, just multiplied by dx both sides if you like. I can bring things up and down on both sides if it's multiplied. Okay, so what we can do, let me bring this down, right, on the left hand side, or just divide by that. So you'll end up with dv over v squared plus 4, right? And then I'm going to bring x on the other side, but divided by x, right? Or let's say divide both sides by x. So you will end up with dx over x, and then you will put your integration sign and you start to integrate. Okay, obviously you need to be a shark of integration in order to master differential equations. Okay, so you need to be very good in integration, and yeah, and then I can support you on that, but yeah, so it's dv by v, so dv over v squared plus 4 equal the integration of dx over x. Now the right hand side actually is easy because we have 1 over x, so the integration of 1 over x is just ln x, or basically ln the absolute value of x, because we cannot have negative number inside the ln, right? And then okay, I can put the constant here plus c for now, but then we have to look at this integration here together and try to solve it, like dv over v squared plus 4. Okay, so let me share the data booklet. Okay, so now if you look at the data booklet, the formula booklet for IB MAA, so you may find, so this is the formula booklets here. Okay, so let's say okay, topic 5, calculus. Right, now all of these are derivatives. Okay, now standard integrals, this is SL, now high level. Okay. Okay, so if you look here, like you may say, okay, this form like dv over v squared plus 4 might be similar or can be, approached by this form here, 1 over 1 plus x squared. Because arctan of x, right, the derivative of arctan of x is 1 over 1 plus x squared. So the antiderivative or the integral of 1 over 1 plus x squared is going to be arctan of x. Okay, so this is probably what I'm going to do, or this is the form, the formula that I'm going to use now. But before using the formula, I need to do maybe some manipulation to apply this law, right? So let me work on the side here. Okay, just different color as well. Okay, so we have the integration of dv over v squared plus 4. Now, first of all, I had 1 plus x squared. So here I had 4. So first of all, I would like to make this 4 1. So how to do that? Easy. We can take 4 common factors. So I will keep dv up here. I will take 4 common factor from the denominator, open a bracket. Now v squared is going to be v squared over 4, right? Plus 4 over 4 is 1. So now I have 1. And then this 1 over 4, it's a constant multiplied. So take it out. Okay, so any constant in the integration, my tip here, take it out. So I have 1 over 4. Okay, just to minimize the confusion. So in the integration of dv over v squared over 4, maybe I can rewrite this as v over 2 all to the power of 2 plus 1. So now it is very comparable to the integration in I just showed you, right? So we will say 1 over 1 plus x squared. Okay. So instead of x squared, or instead of x, I have v on 2, v divided by 2. So here we can use substitution, right? That will be a longer way. Or if you could use inspection quickly, so we can always divide by, because here is the constant, right? So instead of v, you have v, or v times half, right? So if you integrate and you have just a constant multiplied by the variable, you just divide by that constant. Okay, so what I'm going to do here, I'm going to just use inspection here. So I will say 1 over 4, okay, and then divided by half, or basically times 2, okay, and then it's going to be arctan or 10 minus 1 of v over 2. Okay, I had to multiply by 2 or divided by half because I had here v on 2, not only v, right? That's why I did that. Okay, so here is going to be 2 over 4 is 1/2. So this is the final answer, 1/2 arctan of v over 2. So I can now substitute in my main differential equation now. So I can say, okay, so the integration of all, like the left-hand side, is going to be 1/2 of arctan v on 2 is equal to ln absolute value of x plus c. Okay. Then remember, actually we started with x and y, so I have to always come back to x and y. So, and it's now we have v. So here I have to replace v by its substitution as y over x, right? So let me do that. So I'm going to continue here. So we have 1/2 times arctan of v over 2. So now v is going to be y over x over 2. So basically y over 2x, right? Like y over x over 2 equals ln absolute value of x plus c. Now, here is the best time to use the initial condition given in the problem. Okay, so I have here condition when y equal to, okay, x equal 1. So this is the best time to substitute to find the constant of the integration. Okay, so say okay, so let's do that. So when y is equal to 2, x was 1, so 2 over 2 times 1. Now ln absolute value of 1, which is 1 plus c, right? Now I can cancel 2 with the 2 here, so I end up with arctan of 1. Now arctan of 1, what is the angle whose tan is 1? Obviously pi over 4. And of course here we use radians every time, like this is by default. You use radians if you work with differential or integral calculus. Again, you use radians all the time. Use radians if you work with differential calculus or integral calculus. So, okay, so I have 1 over 2 times pi over 4 is equal to ln 1 is 0. So this term is gone, right? And that is a constant. So implies the constant is basically pi on 8. Okay, now I can go back and substitute the constant. So now we have 1 over 2 arctan of y over 2x is equal to ln x plus pi over 8. Okay, now we need to find y. Now this is called a particular solution. So if we didn't have the initial condition like that, y equal 2 when x equal 1, you will actually keep the constant, and what you actually get is called general solution. So YGS, general solution. But here we have a particular solution of the differential equation because we know certain condition and we applied them to find the constant of the integral. Okay, So now my target now is to find y as a function of x, right? So let's do together. So I can basically multiply it by 2, both sides here to get rid of that half. So I can say arctan of y over 2x is equal to 2 times ln x plus 2 times pi on 8, which is pi on 4. Now, in order to get rid of arctan, because I need y only, so you can tan both sides, right? So we can say, okay, so tan of arctan, because it's like the inverse function. So tan of arctan y over 2x is tan all of this, whatever on the left-hand side or right-hand side. So 2 ln x plus pi over 4, right? So tan arctan is basically whatever left. So y over 2x is, okay, tan this term here. So y particular solution, or okay, is equal to 2x multiplied by tan of 2 ln x plus pi over 4. Okay, so we are done. So this is the solution of the differential equation. Started with recognizing it is homogeneous differential equation, and then we used the substitution y on x is v, and then we converted into a separable differential equation, and then you used your skills or your integration skills to finish up the question. Okay, by this I conclude my video for today. I hope it was useful. Please feel free to leave any comments, questions. In the meantime, have a nice day.